Okay, our second talk of this morning will be given by Paul Todd from Oxford, and he'll talk about the twistor theory of the Chen-Teo metric.
Thank you, Maciej. I should say what a pleasure it is to be back in these hallowed halls. If I had my time again, I would change the title slightly. This is much more the twistor construction of the Chen-Teo metric. There's a method of construction that comes out of twistor theory which will give you either Lorentzian stationary axisymmetric Ricci flat, or Riemannian, when it's much more common to be toric, but still Ricci flat. And it has only becoming apparent to me fairly recently that not everybody knows what the Chen-Teo metric is. So let me say, first of all, it is Teo and not tau. It was a bolt from the blue about 11 years ago, when it was a new, as they said, asymptotically flat gravitational instanton, which in this context more or less meant toric, Ricci flat, asymptotically flat. And once you've got such a thing, you can then riffle through your back papers and find the twistor construction for such things, and see how it fits into that picture. And that's essentially the game. So here's the abstract. And about 30 years ago, these people, Richard Ward, Nick Woodhouse, Lionel, who's here, James Fletcher, produced the twistor construction of these things. So as I said, it's stationary axisymmetric spacetimes, so that's Lorentzian, or Ricci flat four metrics with toric symmetry, where I'm thinking that is Riemannian, and you can construct such things in terms of holomorphic vector bundles over a reduced twistor space, and I shall have to say what the reduced twistor space is. And when you've done the construction, it focuses attention on a patching matrix for this vector bundle, and there are, as it were, four of them, but there's one which has got all the business in it. And it focuses attention on that as being the basic datum of a solution. So the actual metric could be a nightmare of formulas, but the idea is that it's all there in the patching matrix, which is a bit easier to think about. So the construction focuses attention on the patching matrix, and then it's a question of interest to catalogue these matrices for known solutions. So somebody comes along and says, look, here's the Kerr solution, what's its patching matrix? Here's the Taub-Nut solution, what's its patching matrix? And you can make a little catalogue, and there have been at least two of these in the 30-odd years that the theory's been around. And it becomes timely now because you want to make it up by including the Chen-Teo metric, which is it's already 9 years old. I mean, in fact, it's already 13 years old. And along the way, what's new in this is something that I did with Maciej not so long ago. Okay, now onwards. So, what is this twistor construction of black holes or gravitational instantons? Well, it relies on two things which are really rather different. And the first one is due to Richard Ward, which is the solution of the anti-self-dual Yang-Mills equations on flat space, or a bit of flat space, as it might be. And what Richard gives you is a correspondence between those and holomorphic vector bundles on CP3, or a part of CP3. CP3 being, in this context, projective twistor space. But they're not just any old vector bundles, they have to be trivial on lines, and when it says lines here, that means the complex projective lines inside CP3. So there's one bit of the story, how Richard gave you this one-to-one correspondence between these two things. But that's very definitely anti-self-dual Yang-Mills, and it has become the case that twistor theory is good at solving anti-self-dual field equations. But you're not interested here in anti-self-dual field equations, you're interested in the genuine Einstein equations, Lorentzian or Riemannian, and there's no expectation of anti-self-dual in there. So the second part of the story is due to Lou Witten, who's father of the more famous Ed. And Lew Whitton obviously knew that the Twistor people should feast on what it was he said, and indeed Richard Ward picked it up. And what Lew Whitton pointed out, and this is very end of the 70s, beginning of the 80s, that the Einstein vacuum equations for a stationary axisymmetric four-dimensional black hole, so he was thinking Lorentzian, the Einstein equations, you can boil them down in a certain way. Well, it was known that you could boil them down, but what wasn't known was that then you could make them look exactly like the static, so I'm making the distinction stationary, static. Stationary in relativity speak means you have a time-like Hilling vector, but it's allowed to twist. Static in relativity speak means it's not allowed to twist. It's still a time-like Hilling vector, but it's not allowed to twist. So static axisymmetric anti-self-dual Yang-Mills in flat space, i.e. in Minkowski space. So what Lew Whitton said is, look, here's a coincidence. The Einstein equations, no assumption of anti-self-duality for this particular case, and the Yang-Mills equations, where there is an assumption of duality for a corresponding similar case, same equations. Okay. So if you put those two together and say, ah yes, but now I remember Richard Ward has told me how to solve the anti-self-dual Yang-Mills equations by a vector bundle, then you should expect to be able to solve the other guy. And the other guy was the Lorentzian stationary axisymmetric vacuum. You should be able to expect to be able to solve those with a vector bundle. So what I'm going to do is review the construction which leads to gravitational instantons, and then give you a bunch of examples, working my way through to the Chen-Teo metric. And the Chen-Teo metric, that's where you'll find it. There was an earlier paper by them which just gave the asymptotically flat Riemannian gravitational instanton, and a later paper when it was sat inside a bigger family, and this is the later one where it's sat inside a bigger family, where you've still got to worry about conical singularities. And in point of fact, I'm going to be a bit negligent of conical singularities. They can be handled, but I'm not going to bother with them too much. Okay, so a sketch of the outline. These are the 5 topics we're going to cover. First of all, a bit of background on twistor theory, and once again, mostly what you'll get from this is the simple pleasures of recognition, because I'm sure most people would have seen it before. A little review of the Ward construction, and then when it comes to the Ricci flat metrics with 2 commuting symmetries, the crux of the matter is the rod structure. So I'll talk about the rod structure and how it fits. And then putting these two together, Ward tells you to look for vector bundles, and so putting them together, the patching matrix is the key thing, and then a bunch of examples. Oh, there's a clock that counts up, and there's a clock that counts down. Right, so there's my sketch. So now the really quick canter through twistor theory, and doing it this way, I'm following Maciek's book. This is not the way that Roger Penrose, for example, would give you the intro, but Maciek's book has a nice way of doing it. So you're going to start with this flat metric on C4, so Z, Z tilde, W, W tilde, they're your 4 complex coordinates. And there's a thing which looks quite a lot like the volume sitting underneath it. And the reason for doing this is that it contains the subcases that you care about, the flat, real 4-dimensional thing, which I'm going to call E for Euclidean. And you get that one if you impose those conditions, and there's the volume. Or you could do Minkowski space with 1 plus and 3 minuses, and you get that one if you impose the next line of reality conditions. Then the omega is then imaginary, so I omega is the volume. And then the point about doing it this way is that you can make a little list of the self-dual 2 forms, and there they are, and they're going to be complex if you're in C4 or Minkowski space, but they don't have to be complex if you're in the Euclidean. Okay, that's the elementary bit. And then alpha planes. So if you've got your coordinates, the big Z's and the big W's, and you take these two linear equations with complex coefficients, that's a hyperplane, the next one's a hyperplane, they meet in a two-plane. That two-plane is an alpha plane. That's what you mean by an alpha plane. As long as alpha and beta are not both zero. So and what's notable about them is that their normals, two forms, are self-dual. So there's self-dual two planes. And you can tell by looking at it this way how many you've got, because alpha, beta, gamma, delta, obviously out proportionality is going to give you an alpha plane. So that's a C4 over the proportionality, which is a CP3. And that's a bit slack because I've left out a bit. I've left out the bit when alpha and beta are both zero. But you can put them in because they correspond to alpha planes at infinity in the Minkowski space or whatever it might be. So I'm going to put up with being a little bit slack about that being CP3, and I'm going to call that projective twistor space. That's the PT. And a little bit of the correspondence, if you've got, instead of a space-time point, loosely spoken of a set of four coordinates, and you look at the two equations at the top, well, that's now become two linear equations on alpha, beta, gamma, delta. And so that's those two linear equations, their common solution is going to give you a CP1 in the projective twistor space. So you have this double vibration picture, which is where mathematicians typically start, and I'll just put it here so I've got it. So down here, I've got my C4, and that's the space of the coordinates. And over here, I've got my PT, and that's the space of the alpha, beta, gamma, deltas. And then up here, I can have my space of these guys, which we'll just call ZAs.
Maybe you want square brackets on the right to say it's up to projective equivalence?
This one? Yeah, for sure. Okay. Yeah, so it's just the proportionality class. And then up here, I've got the Z's and the A and the B, and there are projections like so. And this is crudely the double vibration that gets twistor theory on the road if you're going to do it carefully. And it's worth putting a little bit more in. If I've got a point over here, then it's going to correspond to a line over here. And if I've got a point over here, it's going to be an alpha plane over here. And that's the sort of to and fro correspondence that is one of the nice features of this. Okay. Right, I've done that bit. So you can do it all with indices, and once again, I'm going to be a bit slack about this, but if you write the coordinates as a 2x2 matrix and the spinors as two-component vectors, then the two equations of the alpha plane with the A, the A is the free index in there, and that's having its two values. And the only reason for wanting to do this is that so I can smuggle in the idea that the derivative with respect to the coordinates looks like that. And then the differentiation tangent to an alpha plane corresponds to picking a pi, and the two directions tangent to it are the pi nabla. So if you've got something that's constant on alpha planes, it's annihilated by pi nabla. Okay, now that's the end of the twistor background. So now we shove on to anti-self-dual Yang-Mills. There's going to be five pages of this, and here's the idea. actually I can do if the microphone will stretch. Suppose you've got a Yang-Mills connection on a bundle over the C4, or in fact over a bit of the C4. So I've got a bit of the C4, and I've got the Yang-Mills bundle on it, and it's anti-self-dual. That's the assumption. So it's anti-self-dual, and that means on alpha planes it's integrable. The connection is flat, so I've got a vector space of solutions on the alpha plane. Oh, well, that gives me a vector space of solutions above this point. So there's a corresponding bit of this with another vector bundle over it. And it's got another property that if you restrict it to one of these lines, well, that's a particular point, and you're looking at all the alpha planes through that point, but you've got a vector space of solutions on this alpha plane through that point, and ditto on any other one, so you can glue them all together, and the bundle's going to be trivial. So the bundle that you get from E, namely the E tilde, is going to be trivial on lines, and that's the key bit behind Richard Ward's construction that says don't talk about the Yang-Mills bundle on space-time, talk about the corresponding bundle on the twistor space. There we are. And Ward's result is there's a one-to-one correspondence between them. Okay, well, that's a fairly standard bit. But you want to know if it's one-to-one. Well, I've told you how to get from the left to the right. I've got to tell you how to get from the right to the left. If you start with the bundle, how do you get back to the potential? So that's this. I'm calling it curly E here and E tilde there. That's the same thing. And you want to get back to the Yang-Mills potential. So you take your curly E, you restrict it to one of these lines, then it's trivial on this line. It's got a transition matrix by virtue of being a vector bundle. Restricted to here, the vector bundle is trivial, the transition matrix will split, and that's the GLR turning into a product of a bit on, as so to say, the left-hand end of the line and a bit on the right-hand end of the line. That's what the displayed equation there is telling you. And now, if you do pi nabla times the big G, you're going to get 0, because that's constant on alpha planes. And applied to the line above, you diddle about with the line above, and this expression, which is global which is defined on the left, and this one, which is defined on the right, are the same. And if they're the same, then they're global in the pi, which takes you up and down the line, and their coefficients are a matrix valued one form, and that's the potential. So this is absolutely typical twistor theory argument, though back in the day it was startling. And that's how you go from one way to the other. Right, okay. Where should I be? Onwards. So the third bit about this is Yang's equation. Now I've got a little bit of spinner notation here, because what I want to do is find a nice way. I've avoided writing down the Yang-Mills equations, but there's a nice way to write it down. So you choose a dyad, which just means a basis, but normalized, so they're in a product that way around to 1, then you get 2 sets of alpha planes, because all the ones with constant omicron are stacked up like this, all the ones with constant iota are stacked up like that, and on both of them, the connection is flat, so you can find an H, that's a matrix of sections which are constant on the omicron ones, and an H hat, and that's a matrix of sections which are constant on the iota ones, and you stick them together like so, and call it the Yang matrix. Then the claim is this simple derivative of the Yang matrix with a couple of spinners on it, that is a potential which is gauge equivalent to the one you first thought of. So that it's quite a slick way, and this is evidently due to Yang. This is quite a slick way of coding the anti-self-dual Yang-Mills equations. Well, we haven't yet got the equations, so what are the Yang-Mills equations applied to J? And that just says antisocial Yang is then equivalent to Yang's equation as an equation on J. So it's very cute. And that was in the literature. And then Lou Witten says, now, wait a minute, if we look at solutions independent of, because this is, at the moment, this is in Minkowski space. So we know what phi is, that's a rotation, t is a time translation. Look at the solutions which are independent of those, then the equation at the top of the page, with all that spinnery stuff on it, collapses into this rather cute non-linear, but nonetheless it looks an awful lot like a wave equation, this non-linear equation for the J matrix. And that is then the antisocial Yang-Mills. Now that's quite nice, but the point about it is going to be that it's precisely the same as the Einstein equations with those symmetries. The Einstein equations were a little bit more, so it's not precisely the same. It's the business end of the Einstein equations. We'll come to that in a minute. But here, first of all, now that equation, what are you going to call it? Well, it's extremely tempting to call it Witten's equation, because I think he wrote it down first, but it tends to be called Yang's equation, because it's the one at the bottom of the page is just a special case at the one at the top of the page. Now, what does that do to the picture over here? You've got symmetries in here, and that's Killing vectors. So you've got Killing vectors, and Killing vectors obviously move the alpha planes around. So the Killing vectors over here move the alpha planes around. Well, in that case, they define vector fields over here. Now over here, so I need a place for them, so I'll do it like this, which is probably a bit slack. Here are the two Killing vectors. I can factor this out by two Killing vectors. This is 4-dimensional. I'd factor it out by two Killing vectors. It would be 2-dimensional. There'll be a reduced space-time over here, which is just 2-dimensional. And you ought to be able to play the same game over here that you've got, and you can factor this by, let's call them K and L, vector fields which correspond to the Killing vectors on space-time. And you'd like to be able to factor it by that. But of course, the bad news is that they're not such as to give you a nice manifold. When you do that, they give you, because remember, this guy is just 3 dimensions. You factor it by two vector fields, you ought to get something 1-dimensional. There ought to be a 1-dimensional complex manifold over here, obtained by this factoring, and indeed there is, but it's not Hausdorff. And everybody knows that you avoid non-Hausdorff things like plague, and people would come up to Roger at the time and try to tell him that non-Hausdorff manifolds were the work of the devil, and you shouldn't go anywhere near them. But Woodhouse and Mason told you that you should be relaxed about it. And you can define the thing. So I'm going to tell you what it is. Now, I'm not going to at all try to justify this. You've got to go and look at the Woodhouse and Mason paper. Let me just get my diagram. Well, you're looking for a 1-dimensional complex manifold, and what Woodhouse and Mason tell you is that you can make it out of 2 copies of a CPU, two copies of a complex projective space. So this is going to be a rather crude, that's going to be a CP1, so let's call it P1 on the left, and this is meant to be another CP1. Okay, so I'm drawing it in terms of a 2-set cover, if you like, and that's the one on the right. And so if I call these U0 and U2, and then I call these U1 and U3, and now Woodhouse and Mason tell you what you've got to do is you take something like, as it were, inside the Arctic Circle and stick it there's a bit of this inside the Arctic Circle. And then, of course, that's not going to be Hausdorff near the edges of it. But you just stay completely relaxed and do it again for Antarctica. And you've got a non-Hausdorff Riemann surface, and you can look at bundles over that. And I've got a 4-set cover, so I've got however many patching matrices that is. Most of them are not tremendously interesting, because the patching matrix between this one and this one, just telling you what your vector bundle is restricted to a P1, some line bundles. Over here you get another one, some line bundles. It's this one which is relating, let's say, P2 to P3. That's where business is. Now, P0 to P1, you could think of it as the business as being there, but obviously these are rather simply related to each other by whatever the sum of line bundles is on those two places.
So real structure interchanges Antarctica with the Arctic region if you have a real structure?
You got me there.
I think in the Riemannian case, that's what.
Yeah.
So that in particular, the patching in the northern region is really the one in the southern region just.
Yeah, exactly. So the data, the information, is in that single patching matrix. Yeah. So let me move on to this on the screen. So the space-time symmetries give polymorphic vector fields on the PT, but they have zeros. And so, well, so the quotient, among other things, yeah. So the quotient is a one-dimensional non-Hausdorff complex manifold, and it's curly R. So let's call this curly R. And then the E, which is the vector bundle over this, is determined by these. I've given you the atlas. It's given by the patching matrices. And so when I just say the Weyl patching matrix is that one. Now that's the end of the anti-Yang-Mills stuff. And therefore the ward correspondence. Now here comes the change of topic. So change of topic. Think about this is Lorentzian, stationary, axisymmetric, and then vacuum in the sense of Ricci flat. And suppose the Killing vectors are dBdt and dBd phi. You can split the metric up as a 2 metric at the beginning with just the H, and then there's a J, which is a matrix of the inner products of the Killing vectors sitting at the end. Suggestively called J, because we've already seen a J. Now, where's the rod structure? So, actually what I ought to do is write this metric. Now, if I'm Lorentzian, and especially if I did my PhD in Oxford, the signature is +1 and 3 minuses. So this, the bit at the beginning is going to be some 2 metric, conformally flat 2 metric, and then the bit at the end and the T is the time translation, the phi is a rotation, so the J is indefinite. That one's indefinite, this one's negative definite. Okay, now what do the Einstein equations look like for a thing like this? How do you set about solving them? Well, the first thing you do is you look at the determinant of the J, and J is negative definite, that's negative. So you switch the sign, and you take that as a coordinate r squared, and you find that it's harmonic with respect to this bit of the metric, so you can use it as the first bit of an isotropic coordinate, and you can take its harmonic conjugate as the second bit. And then the beauty of this, and these are obviously, no, these are historically tend to be referred to as the Weil-Papa-Petru coordinates, see how unique they are. R up to sine is just fixed by J, and Z up to an additive constant is then fixed by R. So they're extraordinarily natural. We've got to figure out the Einstein equations, and they're going to involve J, just as they were before, and then a separate bit which gives you omega in terms of J, which we essentially never really worry about. Now, that's for Lorentzian. If you're going to be Riemannian, then J is positive, so you don't need that. And the whole thing is positive, so you don't need that. So there are sign changes when you go over to the, when you flip the signature. Okay, now 0R, you're sort of thinking of this as being the half space of all the Z's, but only the positive R's. And the 0R is the place where the rank drops on J.
That looks like a gamma, but it's an R. Is that on the?
Yeah, that's an R. I could. Okay, then I have to do that one. Now it looks like a V. So the axis of 0R, well, it's in the RZ plane, so you can play around with it. But I'm going to take it to be a straight line, and on that straight line, the rank of J, the determinant vanishes, so the rank of J certainly drops. With most of the places on that axis, it's going to drop by 1, but there will be occasional points where it drops by 2. In other words, the matrix completely vanishes. So the axis is split up by isolated points, intersections. The section between, now I'm going to call them nodes. In the literature, they have all kinds of names. Some people call them nuts, which in this context tends to be used for something else. Some people call them turning points. Well, let's just call them nodes. A section of the axis between adjacent nodes, that's a rod. And next to the rod, you can write which Killing vector vanishes at it. And then for the Lorentzian case, rotations will vanish. But when you get to the horizon, nothing vanishes, but one of the Killing vectors becomes null. Now, when you do Riemannian, that's a distinction that you don't have to worry about. And also, so we're expecting to get a line with a certain number of nodes on it, dictated by the solution, and then if you're asymptotically flat, or asymptotically locally flat, or asymptotically Euclidean, or asymptotically locally Euclidean, then at the end there'll be semi-infinite rods going on forever.
So if you take the quotient by S1, then you get the usual toric diagram where the rods become edges and the nodes become vertices. Exactly.
And there's and if they don't go on forever, you get a polygon. Yeah. So a lot of that theory is hiding behind it. This is from a paper in the, not by me, by Hallmark, in the relativity literature. So so one could, well, wouldn't it be convenient if we all use the same terminology? There you go. So I'll give you an example, and this is pretty much the simplest example. This is 4-dimensional Euclidean, and I'm writing it as the sum of 2 sets of plane polars. So U and phi, that's a plane polars, V and chi, that's a plane polar, 2 sets of plane polars, let's see, 4. And then let's do the business. You take the determinant of J, and that'll say now R squared. Now this is Riemannian, so I don't need the minus underneath J. So R squared is U squared V squared, so R is UV. And then you can do the harmonic conjugate to that with the flat UV metric in your head, and there it is. It's Z, where I haven't added a constant. And so I'll draw its picture. And it's about as simple as you can imagine. In the middle, where U and V are both 0, which is the origin in these coordinates in E4, you've got the node, and then the top part is where the chi vector is 0, and the bottom part is where the phi vector is 0. And that's the rod structure. And if you've got anything which is AE or ALE, it'll have some slightly different bit of junk in the middle, but on the outsides it's going to look like this, with different kilivectors at the top and at the bottom. So there's a nice easy example. And here's another nice easy example, a Schwarzschild, so let's call that one E4. So this is a Lorentzian Schwarzschild. So you look that up, find out what its metric is, do the stuff to tell you the Weierach-Petre coordinates, and there they are, R and Z. And now, can you look at the rod structure for this? Well, if you look at the definition of R, the theta can vanish at naught, and the theta can vanish at pi. And also, if the big R is 2m, m is positive, so that one's, as it were, outside. If the big R is 2m, the little r will vanish. So you're going to get the bit up here, where theta is naught, the bit down here, where theta is pi, and for both of those, the d5 vanishes. And then the bit in the middle, where r is 2m, that's where the dt is null. Now, if you've got anything which is asymptotically flat or asymptotically locally flat, then there's junk in the middle, but it'll have this kind of thing on the outside. So the difference is that it's the same vector on the two semi-infinite bits. This one's got the opposite. So you're straight away going to recognize the two things. And then there's a theorem. Now, this one is from Hollands and Yazdayev, and it's in dimension 5. There must be a thing in dimension 4, but I couldn't find a reference for it. That if you know the data consisting of the rod structure and the asymptotic quantities, because, for example, here you've got an asymptotic mass. If this was Kerr, you'd have an asymptotic angular momentum. And the idea that you must have is the asymptotic quantities and the rod structure fix the solution uniquely. And as I say, Hollands and Yazdayev did that in 5 dimensions. But
so if you did this for Riemannian Schwarzschild rather than for Lorentzian Schwarzschild,
yeah,
what are the differences?
So that becomes
0.
Yeah.
That's like the only difference.
Yeah, because exactly the T becomes periodic, and that makes it a toric thing, and yeah. Okay, right, so now I'm going to go back to the Yang equation for a bit. Let's remember the metric form up there. Now for these metrics, i.e. with the two commuting symmetries, or their Riemannian counterparts, the Ricci-flat conditions are precisely the thing that Lou Ritton got from the Yang equation. So there's the J, so we know what J we're talking about, and it's the top line, the top equation there. And as well, there's an equation for the conformal factor, the omega, but it's, I've written it this way so that you can get it on one line. I've introduced a new complex variable that's Z plus IR, and these are W derivatives. So split it into the two real bits, and that's the way you'd normally find it in the book. But it's integrable on the basis of the equation at the top, so we really don't mess about with it, except when we want to worry about conicality. So the challenge then is to adapt towards correspondence to solve which is designed for static axisymmetric Yang-Mills, anti-subdual, adapt it to this. There's the challenge.
So in terms of the way that omega is determined by J, there's a constant of integration, but it's just a multiplicative factor.
Exactly. It's additive in omega, so it's, log omega, so it's multiplicative sitting out the front there.
And so it doesn't change the solution, it's just rescaling it.
Pretty much, but you've got to get it, well, in a certain sense, you've got to get it right to get rid of conical singularities, because it's telling you the radius, the proper radius, and which you've got to get right with whatever you've chosen for the periodicity. Yeah. Now, before you do that, there's another step which was known in the 60s as the slick way of trying to make progress with these, and that's the following. If you pick on the kilivector dBdt, which will be the one you cared about if you were out here, then if you take K wedge dk, that's a 3 form, star it, that's a 1 form, the Ricci flat condition tells you that's closed, and because of everything else, it's exact. And that psi is what, well, it's Ernst, I think, Fred Ernst who did this first of all. Now, if you know that psi, well, if you work it out, if you work out that psi, you can define a different J matrix. And it's got the psi in it, but it's also got the capital U. Now, remember, back a little way, the capital U is just the norm of the Killing vector K. So concentrating on one Killing vector rather than another, you can make a J primed. And the remarkable thing about it is that it still solves the Yang equation. So what this is it's a slick way of turning one solution of the Yang equation into another one. And that's why it's a Vectrin. That's why it's a Vectrin transformation. Part of the payoff is that the J prime has got determinant 1, whereas the J, remember, had determinant R squared, which therefore varied from place to place. Okay, so I'm going to call that matrix the Ernst potential determined by K. The thing which historically was called the Ernst potential is the complex function U plus I psi, and then Ernst wrote down an equation on that. Now this is for Lorentzian. If you want to do Riemannian, you juggle the signs a bit, but let's not worry. Let's not worry too much about that. Right, so now we're going to bring in the rod structure. And so the deal here is, once you've decided on a Killing vector, you can make the J prime. Here's a rod structure. So you say, well, I'm going to look at this rod. That Killing vector is 0, so I'm not going to choose that one. I'll choose the other one. I choose the other one, I can make a J primed. Down here, if it was Riemannian, that Killing vector is 0. I don't choose that one, I'll choose the other one. And I can work out another J primed. I come down here, I work out another J prime. I can get a J primed for each rod. So suppose we've got the rod structure, somehow we know what Killing vectors are, and on a rod where L vanishes, or is null, you construct J prime from K, and then the payoff is that the P matrix that we've been struggling for is that J primed on the axis. And so it's still a function up and down the axis. Now, I'm not going to prove that. It's in the Fletcher, Woodhouse, Mason-Woodhouse papers from 30 years ago. Now, when you get to the end of the rod, remember you're going to get to a node, and when you're at a node, both Killing vectors are 0. So when you get to the endpoints, the J primed is going to be singular, because if we remember, the J primed has got a 1 over U in it, and when I get to the node, U is going to vanish, so the J prime is going to be singular. But along the way, it's not. Everywhere else, it's going to be perfectly analytic, in fact. Oh yeah, and I said, well, dvd phi is null, I'm obviously going to choose dvdt. Well, okay, I could have chosen dvdt plus 28 times dv phi instead as another Killing vector, but the idea is going to be it's an equivalent thing. So I'm going to generate a P on each node, that's what I'm going to do, and then the singularities in them, the P on this node will become singular on this rod, will become singular at that node. The P on this one will be singular at both ends, the P on this one will be singular at that end. Okay. But they can only be simple poles. Why is that? Well, because if they were double poles, then if you chugged through the splitting, which I alluded to, you'll get space-time singularities. So your P is not allowed double poles, but it's inevitably going to have simple poles. And what about if it had poles at a complex value of Z, because we're running up and down here, Z is actually real. Well, if P had a pole at a complex value of Z, it would mess up the splitting again and give you a space-time singularity. So your P, one thing you know for sure, is that it can only have poles at the nodes, okay? And then the outermost P's, well, they've got some parts of them fixed because you've got to have your asymptotic quantities. So if we can do a little calculation, let's take the most general asymptotically flat Riemannian, look up in a book, you'll find an expansion, this is Riemannian, you'll find an expansion for the UVW, the J matrix. Therefore, you can work out your bar-Pepper-Petro equations, you can work out your twist potential, you can work out your J primed and your P plus, and it has to look like that. So it's leading bits. Well, it's really leading bits as you go a long way up the axis. You've only got the 1 and the -1. Now this is Riemannian. If it was Lorentzian, you'd have a 1 and a 1. So a standard form at large distances. And what's more, the next terms that come in are driven by the asymptotic quantities. Okay.
In the Riemannian case, at the nodes, both killing fields have to vanish.
Exactly.
Is that not true in the Lorentzian case?
Well, because of the null, yeah. If it was Lorentzian Schwarzschild, you hit this one, that guy vanishes, and that guy's null. Yeah.
That's all you know.
Yeah.
So what you know about the twist potentials is weaker. Is that right? So in the Riemannian case, the fact that you have one of these nodes will guarantee that if you look at the orthogonal complement of the torus action is actually an integrable surface.
Well, but you can do sort of expansions about the node, and the Lorentzian and the Riemannian are pretty close together, close enough together that you can treat them. So this is what the Riemannian one looks like, and we sort of knew that it had to look like Schwarzschild, and I'm telling you, that there is more like Kerr, obviously, because it's got angular momentum. What about the asymptotically Euclidean? Well, you can't now go and look up in a book and find out the expansion of the general Riemannian, but you can diddle about with something that is in the literature, and I claim this is the expansion, the general expansion. It's got conserved quantity in M and L in it, but they shouldn't be thought of as mass and angular momentum because, after all, it's not the right asymptotics. But you can still work out the Pepper-Petro coordinates, the twist potential, and the P plus when you're way up the axis. It's totally different. This one is growing, and this one is decaying, and that's what asymptotically Euclidean looks like. So it's a bit hard to manage, and the other constant sits off diagonally there. But nonetheless, there's a canonical, if you like, thing they look like. Okay, pressing smoothly. Oh, this was if I wanted to do Schwarzschild right through to the end. I've got enough information now. And if it's Riemannian, this is what they look like. So the nodes here, the Z value of the nodes is M and minus M. And sure enough, the only place you can be singular is at the nodes, but as you come down, they shuffle about. So the one in the middle has got to be singular at both ends, as it is. The one at the top has only got to be singular here. It's got to be singular here. Of course, it's determinant, it's got to be constant. And the one at the bottom has got to be singular here. So that's just, and there's a similar thing for Kerr, but I need to watch the time. Because one of the issues is, how do you go by a node? I know how to work it out here with the aid of dBdt, and I know how to work it out here with the aid of dBd phi, and we saw the picture. As the singularity structure changes as you go by. How do you code that? And the answer is, and this is in Fletcher's thesis, so suppose it's at z equals 0, then P is going to blow up there, but you can always modify it with a similarity transformation so that only the top left term is singular. And then if the determinant is going to work, the bottom right term is going to be 0 in the same place. And then off diagonal, it's holomorphic. And then the rule for going by the nut is you take the pole, top left, and put it in the numerator as a 0, and you take the 0, bottom right, and put it in the denominator as a pole. And that's your rule for going by a nut. So now you see.
Node is the terminology you've been using rather than nut.
Oh, yeah, I thought I corrected that. Yeah, there's nuts and nodes. Now, you can now therefore say, when I'm a long way up here, I've got an asymptotic form. I know the only singularities are at the nodes, of which there might be 19. Yeah, there could be a lot. And down the bottom, I know something. And as I go by one, I know something. And the issue is, have you got enough moves that you can make to fix the p's from the rod structure and the conserved quantities. It's perfectly good. Because then, you see, you don't have to solve the Einstein equations anymore. You can just play combinatorics with the p's. These are going to work. So let's recall, if you like, the general properties of P. And you've always got the freedom to do this similarity because that's, you know, it's a patching matrix. You can always do that kind of thing. If you're asymptotically flat at large distances, you're going to look like the second bullet point. But if you're asymptotically Euclidean at large distances, you're going to look like the third point. You're allowed, or you insist on, simple poles at the nodes, otherwise they're not nodes. You don't want any other singularities, so no singularities off the axis. And you've got a rule for going past the node. And if you're prepared to restrict to ALE or ALF, you know the asymptotics. Now, the only way P can have singularities is by having them at the nodes. So P is going to be rational functions, and the denominators are all going to be the product of the zeros. So this is really strong. Now you can say, oh, let me have a go at classifying these. Make a catalogue. And this is the barest sketch. But if you say, I only want one node, then it can be E4, and there are two ways of making it E4. But it can also be self-dual Taub nut, and that's your lot. If you've got two nodes, there's a whole bunch of things. It can be Kerr, and therefore Schwarzschild, Riemannian or Lorentzian. It could be Taub nut, yeah, absolutely. There's something which is Lorentzian. There's something in the literature called Taub bolt, and this is the reason for not calling these things nuts. That go into that mess. There's something called the Kerr Taub bolt. This is Riemannian, not Lorentzian. There's a Gucci-Hansen, which is self-dual, and there's the next one up the ladder of Taub nuts, because there's a countable ladder of Taub nuts. And there's an obvious room there for another asymptotically Euclidean one, because Gucci-Hansen is self-dual and asymptotically Euclidean, but there's room at the level of playing with the P matrices for having a not self-dual asymptotically Euclidean. And it's worth saying that solution's not known. Now, if you come down to three nodes, things like the C-metric, which is Lorentzian, Blavatsky, Demiansky, these are real, as it were, bird spotters' delight, rare metrics. You don't come across that often. But this is where Chen-Teo is, and then you can have the three singularity of Gucci-Hansen and three singularity Taub nut, which there's nothing to stop you going on because there's an N node Gucci-Hansen and there's an N node self-dual Taub nut. And you could have double Schwarzschilds. Now these, you have two Schwarzschilds with conical singularities, which are always interpreted as struts to hold them apart, or as bits of string to hold them apart. So I haven't talked about conicality, just for the point of time. So now finally, Chen-Teo, it's got to have three nodes. So let's put them alpha, beta, gamma. They're the Z values. Well, the Z values, you can slide them up and down the axis, so I could make them add up to 0 if I wanted to. And here's what the P's got to look like. It's got the delta as a common denominator for all of them. And then in order to get the asymptotics right, the top left has to be a cubic, the bottom right has to be a cubic, and then the other guy has to be linear, and certain coefficients of it are fixed by the asymptotics. So two of the coefficients in C1 are fixed, two of the coefficients in C2 are fixed. Altogether, you've got 5 coefficients that you haven't fixed, but you've got the condition on the determinant. The determinant of P plus is 1, and that's obviously a bit of algebra to make that equal to 1. Now, you could get them by starting from the Chen-Teo metric and doing some mapling, non-trivial mapling, and it'll give them to you. Or you could say, well, let me just impose this condition on determinant. It's a high order polynomial. I'm going to get lots and lots of conditions. I'm trying to fix A, B, C, D, E. And this is something that Maciek and I looked at. And the idea is, it doesn't look as though it forces Chen-Teo on you. It seems to have one more parameter. So on the face of it, there's another solution with another parameter. So this is where Chen-Teo sits, but maybe there's some more stuff as well. I've got 2 minutes. You can extend, I've been doing it for 4, but we actually, a little while ago, Lionel and I had a student in Oxford who was doing it for 5. So the idea is 3 killing vectors, all commuting, and then the J matrix is 3 by 3. But rod structure, wall construction, that all goes chugging through as before. If you're on a rod, 1 killing vector is 0. You've got the other 2 killing vectors, so you've got 2 scalar twist potentials and another formula for the J prime. Going past the nut, well, it's a bit harder, but you can do it. And you can start looking for the known 5-dimensional black holes, like Myers-Perry. Myers-Perry has 2 nuts, so you say, I want 2 nuts.
Nodes.
Huh? Nodes, yeah. 2 nodes. And asymptotic quantities, and beautifully, the asymptotic quantities and the fact of having 2 nodes fixes it for you completely. You can go up to the black ring, which is 3 nodes. Bingo, it's the same story. One of the killing vectors is twist free, so you get some zeros, which save the day, but you can fix the P matrix from the rod structure and the asymptotics. So it works a dream. I should say one of the reasons that Woodhouse and Fletcher were interested in this back in the day was that it was supposed to be another way of doing black hole uniqueness. If you know the asymptotic quantities, it fixes the P. It even tells you where the nodes are. So on the face of it, that's a form of black hole uniqueness. And then one other thing that you could contemplate trying is this was all vacuum. Suppose you do Einstein-Maxwell, and Woodhouse worked this out. And if we do it in 4 dimensions, then the 2J jumps to a 3 by 3 and accommodates the Maxwell potential, and you can play the game there. That's been done much less, I should say, but nonetheless it would seem to be available. Okay, well I'll stop there.
Other questions? Cool.
So you have this harmonic function that's lurking in there as the omega, but what's the algorithm? So if you just know the omega.
When you say omega,
this harmonic function plays a.
That's the harmonic function.
They are.
Yeah, yeah, and he comes from the determinant, square root determinant of this guy, and it's a bit of Ricci flatness that's harmonic with respect to this 2 metric.
Oh, I see.
And so it has a harmonic conjugate, and the 2 metric has to look like that. It doesn't have to have a 1 there, but you subsequently get an equation which tells you that one in terms of that one. Yeah, yeah. But it's sort of, because it's it's a line integral. There's nothing you want to check. You do the line integral. You try and get it right to knock out all the conical singularities, but that's a different story.
But if you're stuck with, if all you know is the harmonic function, you have a Monge-Ampere equation that's. No, it's not complicated. It's not Monge-Ampere.
Well, the J equation, the so-called it was there, wasn't it? Guy at the top. Yeah, it's linearized. It's a wave equation, a Laplace equation. So it's a Laplace equation with a nonlinear term, and the whole rigmarole is to solve it without solving it by twistor construction.
Okay. Other questions? Yes.
So the Chen-Teo metric seems to depend on like a lot of parameters. Is it known or possible to somehow impose some relations that makes the Chen-Teo metric self-dual?
Well, yeah, they tell you, Chen-Teo, not Tower, it was Terence Tower, yeah, it's not him, it's somebody who works with Chen in the Far East. Singapore, and they tell you that you can think of their metric as sitting at a limit. One way it's Plebanski-Demiansky, and the other way it's, my colleague will remind me, 3-pole. Well, I can tell from the, so Chen-Teo limit, it's got, as you say, 5 or so parameters, and there's a limit of it which makes it Plavansky-Demiansky, which is a bit odd because this is asymptotically flat, this is asymptotically Euclidean, and there's another limit of it which makes it, one or other of these, I forget which.
It's this one, yeah.
Yeah, but is it that one or is it that one?
No, it's the ALE free component Gibbons-Hawking, so it must be this.
It's that one, yeah. Yeah. So it does have a self-dual limit. Yeah, but it's the Iguchi-Hansen. You know, Iguchi-Hansen, you pick a potential, which is a sum of poles, and you have as many as you like. And so when I say 3, I mean it's the one with 3 poles.
Ladon?
So do we know how many of those are type D? I mean,
well, an awful lot of them.
Sorry?
An awful lot of them have...
Well, certainly Kerr and Tabnas.
Yeah, the question is, are there any that aren't type D? So the connection that was made at some point earlier on was that type D and Hermitian are closely related. And so you can say, oh, let's find all the Hermitian ones. And this was done by Godeschon and Bicard fairly recently. And Chen-Teo is in there. It's a Hermitian one. Their method insists on regularity right from the start. So the ones that have got, you know, they're never going to see double Schwarzschild because you can't get rid of the quantum singularities. For the same reason, you're never going to see Plavansky-Demiansky. And they deliberately force it not to be self-dual, so you're never going to see these guys. So there aren't so many things you see, and Chen-Teo was the one that was missing. Now I've forgotten your question now. What was your question?
Sorry, it's type D.
Oh yeah, type D. But if it's Hermitian...
One side D, type D on one side, not on the other.
Yeah, if it's Hermitian...
Most of the other ones are actually type D.
Well, if they come from the Lorentzian, then one side and the other side are tied together.
Yeah.
But things like tau bolts don't come from... is that one? Yeah.
Oh, I see. So tab bolt could be one side of type D, but not the other.
It could be, yeah, yeah. Because you only care about one side, that's where the complex structure is. Yeah, and that ditto with Chen-Teo. One side's type D, the other side, Stefan Einstein worked it out, and it's actually type 1. You know.
Reminding tau bolt is both, it's type D for both W plus and W minus, both sides.
Oh, is it?
Yeah, yeah. So the only one Chen-Teo in the Picard-Godeschon classification, but ALF plays a big. The assumption that it's ALF also cuts down possibilities. That may be just really crucial. If you relax that, who knows what happens?
Yeah.
But they basically, so the only one that's not two-sided type D. Oh, actually, no, sorry. That's right. So there's one. The two things that come up that are not type D for both sides are Chen-Teo, and then it's sort of a cheat, tau nut, which has 0 for
the other side. Yeah, yeah.
So it's actually
is that type D or not? Yeah, yeah.
Okay. Let's bank pull again.